Sets of proxy data that I want to show you, and the first is pollen analysis. So pollen is really, really cool because it's the reproductive mechanism of plant matter. And as the reproductive mechanism of plants, it has a resiliency in it that allows that mechanism to really stay intact and viable for long periods of time until the climate conditions are right for it to germinate. So we can have long periods of preservation of pollen, and some really diligent and careful, detailed people over a long, long period of time have paired pollen with particular species. So we can look at all of these different pollen shape and know exactly what plant and or what plant family it belongs to. And because of the plant and plant family, we know exactly what climate conditions this pollen would have germinated under. So lake bed cores, what we've got is pollen, and for those of us who have allergies, we know that pollen will come up and become atmospherically a pollutant and everywhere during the season that the pollen is a problem. And it falls on everything. It's on your cars and in your shoes and on your dog. And so we're always getting a blanket of these pollen every germination season. Now, for many plants, germination happens only once a year, but the ecosystem doesn't want the plants to compete against each other, so it has various germination seasons across a year for the organisms within that ecosystem. So we'll get germination for species A in the early spring, and species B in the mid-spring, and then C in the late spring, and then that sort of trend continues through to fall. So we can get a composition of species that are indicative of an ecosystem, which then is very closely tied to the range of tolerance, what those species can tolerate in terms of heat and moisture conditions and acidity and other variables, currents, wind conditions, for instance. So we get a lot of data out of pollen as a result. So as this material rains down and gets deposited, we can then pull out the range of pollen of different time periods and know what the climate was like, because we compare it to the plants that they are most similar from today's sample sets. Coral is very much the same way, but coral has a very tight range of tolerance. It takes very, very little change in temperature to produce a change in the nature of coral and the viability of coral. So where other plants, let's say like Arctostaphylos uva-ursi, which is a plant in the Arctic and in the tundra area, may be tolerant to many, many degrees of change over time, 10, 20, 30 degrees, it can withstand. Coral can only withstand 1 or 2 degrees in change in temperature. So we can measure the rate of health of coral as it grows concentrically from the bottom up with these polyps over time. So as the health and the vigor of these polyps then are produced, we can look at how healthy they look and start to recognize whether there is a change in temperature or occurring across the water body that this coral lasted in. So we can really get to a fine detail of what the temperature was like under this coral ecosystem conditions. So coral and tree rings are very much the same. And if you take a look at the coral sample in the top here, you can kind of imagine it very much like a tree ring, where this would have been the pith or the early growth. And then we get concentric growth on the way out from the center, just like a tree ring would have grown. And this is annual growth. With the tree ring, we're getting biannual growth.